Welcome everyone. Welcome to the CNCF webinar series. My name is Ihor Dvoretsky. I'm a developer advocate at Cloud Native Computing Foundation and a features lead at the Kubernetes 1.11 release team. And today we'll speak about Kubernetes 1.11, the latest release, the newest one from the Kubernetes release team. Next slide, please. So our presenters today are Jundu and Chris O'Hara from Kubernetes SIG Networking, Michael Taufen from SIG-Node, Eman Kumar from SIG Storage, and Caitlin Barnard, who is 1.11 release communications coordinator, and she'll help us with driving the webinar. This. So with this release, we have around 25 features that add the new functionality to Kubernetes or heavily enhance the existing one. And the most important of them you can see on the current slide, and we'll highlight today at today's webinar with more details. So now I'd like to pass the microphone to Jundu from SIG Networking, who described the new feature called IPVS-Based in-cluster service load balanced. Welcome, Jun.
Hi, hello. Hi, my name is Jundu from Huawei, and I'm the IPVS owner. Glad to see you. Good morning. It's 1 o'clock in China. Yeah. So let's begin. Okay, next the slide. Okay. As we know, the default mode of Kube-proxy is IPTables. So what's IPTables? IPTables is a user space application that allows configuring Linux kernel firewall. Linux kernel firewall is implemented on top of NetFilter. IPTables can configure the NetFilter by configuring the chains and rules. There are five rules and and four to five for the chains in IPTables. Okay, so what's NetFilter? NetFilter is a framework provided by Linux kernel that allows customization of networking related operations such as packet filtering, net means network address translator, port translating, and so on. So everything seems okay with the IPTables, but IPTables doesn't perform very well in large scale tasks. There are two main issues for IPTables acting as the load balancer. There's the latency to access service will become very large when the number of services increase, and the latency to add or remove IPTables rules will increase when the number of service rules become very large. Okay, next. There are some optimizations to the IPTables, but today I want to introduce them. I will introduce the IPVS mode in the project. Before working through the IPTables mode, firstly let's have a look at the IPVS. What's IPVS? IPVS, same as IPTables, it's built on the top of NetFilters. Yeah, they are and IPVS. It's a transport layer. It's level 4. Okay, level 4 load balancer, which directs requests for TCP, UDP, and SCTP. based service to real servers. It's designed, IPVS is designed for load balancing, not for firewall. Okay, and IPVS supports 3 load balancing mode: the net mode, DR mode, and IP tunnel mode. Only net mode supports the port translation. So in Kube-proxy, we use the net mode. Okay, although DR mode very fast, but we use the net mode. Net mode is also very fast. Is yeah, we can almost achieve more than 90% performance number in IPVS mode, compared with the experimental. So why do we need the IPVS? Okay. Firstly, it has better performance because IPVS uses the hard table data constructor instead of the chain. Okay, and there are more load balancing algorithms in IPVS, such as round robin, source hash, destination hash, and it also supports algorithms such as based on list load, okay, list connection, and so on. Okay, we can also assign the weight to each real service. So the so-called weighted round robin, weighted list connection, and so on. IPVS also support server health check and connection try. It natively support stake session finally session staking. Next. We contributed this IPVS mode since Kubernetes 1.8. In 1.8, it's still an alpha version, and in 1.9, the IPVS mode graduates to beta. Okay, and in 1.11, it becomes GA. Okay? To run Kube-proxy in IPVS mode, you only do 3 things. Okay, you need to check 3 things. Firstly, load the required kernel models. You will need to load such kernel models. 1, 2, 3, 4, 5. Okay, 5 kernel models. The IPVS related. And switch since the IPVS mode is still not the default mode. Okay, we need to switch the proxy mode to IPVS. And make sure we enable this feature gateway before 1.10 because before 1.10 it's still in alpha stage. After 1.10, it's in beta, so it's enabled by default. Support the IPVS product mode to true set the product mode. Okay? Next. So let's take a sample. If we Kube-proxy in IPVS mode, Kube-proxy will do the 3 things when a user creates a service. Okay, a service. Firstly, make sure a DOMI device interface exists in the node. The default name is the Kube IPVS name, IPVS 0. Secondly, bind the service IP address to the DOMI device. For class IP type of service, the service IP is a class IP. And for node port service, okay, the address can be the class IP and the node IP. Okay. Thirdly, create IPVS virtual servers for each service IP, for service IP, and create the real servers for each endpoint. So let's see the example next. This is the last page of this share. Okay. Firstly, we create a service named inject service. Its IP, class IP is 10.102 and so on. Okay. And it opens the port 3080. Okay, and it has two endpoints. Okay, as you see. Firstly, we can see there is a Kube IPVS lane, IPVS 0. This is the domain device, and we bind the class IP to the domain device. Okay, and Kube-proxy will create the IPVS virtual servers and real servers for the service and endpoint. If we type IPVS admin LN, then we can see the real virtual server and the real servers. As you can see, the virtual server is in the MASQ, the net mode in IPVS. Okay. Thank you, everybody. That's all. Thank you. You can ask me questions.
Thank you, Jun. We'll have the Q&A section in the end of the webinar. So please prepare your questions before that. Thank you, Jun. So now we'll speak about Core DNS. Core DNS is an independent project incubated currently at CNCF. At the same time, in the current Kubernetes release, it's one of the most important building blocks for the networking stack. So now I'd like to welcome Chris from SIG Networking, who will speak more about Core DNS in Kubernetes 1.11.
Hello, everyone. Let's go to the first slide. So first, what is Core DNS? Well, Core DNS is a standalone DNS server. It's a CNCF incubation project. It uses a plug-in chain architecture, meaning that DNS requests come in and it passes through a series of plugins, and each plugin performs a function on that request. It's flexible. You can combine plugins together for advanced functionality, and it's extensible. It allows you, it provides a framework for writing your own plugins if the existing plugins don't do what you need. Next slide. So that's what Core DNS is standalone, but how does it fit into Kubernetes? There's one plugin called Kubernetes that enables Core DNS to provide DNS-based service discovery in a Kubernetes cluster. It follows the DNS-based service discovery specification that is defined. It can replace KubeDNS because it's functionally equivalent. And Core DNS is an approved alternative to KubeDNS in Kubernetes 1.11. It's also the default in kubeadmin in 1.11. And it's also an option in COPS, not COBS, KubeUp, Minikube, and KubeSpray, and other installers. Next slide. Core DNS fixes a few issues when compared to KubeDNS. There's some open issues that are in KubeDNS that are resolved. Some of these are feature requests. Some of these are bugs. I won't go through all of them, but like allowing custom DNS entries for KubeDNS, the little bug like missing A records in a certain case. Let's go to the next slide. There's some outward changes with Core DNS as compared to KubeDNS. Somewhat minor one is that, at least from a usability perspective, is that KubeDNS has 3 containers CoreDNS has one. From a metrics perspective, they both report metrics to Prometheus, but the set of metrics differ. Part of the reason is because of the one container versus three. From a configuration perspective, that's the biggest change you'll see. There's migration tools available for converting the KubeDNS config map to CoreDNS. CoreDNS is fully configurable via the config map, and KubeDNS is not. That's another difference. Next slide. Here's an example of a CoreDNS configuration. Trying to keep it short here, so I won't go into all the details. But the bottom section there is pretty much what you'd see in a default install from kubadmin. The top section is an example of what a stub domain looks like. That's basically saying everything that comes in on port 53, for example, .com, gets proxied out to 1234, and we cache it for 300 seconds. The bottom section shows health monitoring, the Kubernetes plugin itself with the default settings, Prometheus, which enables metrics reporting, and then the fall through default forwarding everything else through etc resolve conf. Next slide. So to highlight a couple of new features that CoreDNS has, one is verified pod records. Here's an example of what a pod record looks like. And in KubeDNS, all IP style names like that, where you have an IP that's dashed, that it'll return a record, even if that pod doesn't exist. As long as it's a valid IP address, it will say, yeah, that exists, and give you an answer. In CoreDNS, you have the option to only create those records for real pods. And to enable that, you would use the pods verified in your configuration. Next slide. Another cool feature, which is not enabled by default, but you can, if you want to enable it, is server-side searching with Autopath plugin. Not sure if you're familiar with the n.5 problem in Kubernetes, but if you aren't, an example of where that goes badly is when you do a search for an external domain, for example, infoblocks.com from a pod. It's first going to try the namespace, and then it's going to try the next level up, and the next level up, and the next level up. And so what happens is you end up with around 6 exchanges between the pod and the DNS server before you get a real answer. So what CoreDNS does with the Autopath feature is it answers this in one trip. It understands that that odd style query in the beginning is the beginning of a long search, and it just short circuits it and gives it the final answer in one step. One thing that makes this problem worse in KubeDNS is that none of those NX domain responses are cached because there's no negative caching by default. But it is all cached in CoreDNS. Next slide. Some other features won't go into as much detail in. We allow zone transfers for the Kubernetes domain. We have namespace and label filtering, so you can expose just a limited set of your services if you want. You can adjust the TTL up and down depending on your needs. And we support negative caching by default. Next slide. So I mentioned that we're built on a plugin chain. And so there are a lot of built-in plugins. There's 34 when I counted last. A few interesting ones are ones that are used a lot are file. It allows you to serve a zone from a zone file. Rewrite, it allows you to rewrite requests as they come in. Allows you to do kind of behind the scenes aliasing that's invisible to the client. And template, it's great for debugging, for example. It allows you to define responses based on a regex and a Go template. And if you've got other needs that plugins, the built-in plugins don't solve, you can build your own plugins. There's some cool external plugins that other people have built. Unbound uses the Unbound library to do recursive DNS. PD-SQL does will serve records from a backend database. Redis-C will use Redis as a shared cache across multiple CoreDNS instances. And Kubernetes, which is the plural of Kubernetes, in case you were wondering, it allows you to connect a CoreDNS to multiple Kubernetes clusters for cross-cluster discovery. Next slide. Real quick, this is the roadmap. In 1.9, we were alpha, beta, and 1.10. Now we've graduated to GA. We're not the default yet, but we are default in kubeadmin installs. The future goals would be to make CoreDNS the default, replacing KubeDNS, and eventually deprecate KubeDNS. Next slide. There's some links here. If you have any questions or issues or want support, we're very active in GitHub and in Slack for any security related issues. Send to security@coredns.io. Each plugin is documented, and you can find that documentation on the CoreDNS website. And also, thanks to John Bellameric, I pretty much took 99% of the contents of this presentation from his blog, which I've linked here. Next slide, please. Thanks, everyone. And also, we're conducting a survey to try to see who's using CoreDNS and what plugins they're using. There's a link here. Thank you.
All right, thank you, Chris. I'm really excited to see how big progress CoreDNS made during the latest period of time from the easy replacement for Kubernetes built-in DNS server to the default one these days. So besides networking, another major error in Kubernetes is node functionality. And now I'd like to welcome Mike Toffen from SIG-Node, who will cover the dynamic kubelet configuration feature.
Hi, everyone. I'm Mike Toffen. I work in SIG-Node in Kubernetes. In this release, we launched to beta a pretty cool new feature called dynamic kubelet configuration. So if I could just have the next slide, please. So why first, before we get into exactly what it is, why do we want to do something called dynamic kubelet configuration? So just for some history, Kubernetes is built around the idea of offering declarative APIs that are hosted in a central control plane. That's your API server. In Kubernetes, you can use these APIs to configure most things about the system, unless the thing you're trying to configure isn't already represented by a core abstraction of that system. So like most things run in pods, but most Kubernetes deployments don't run the kubelet in a pod. Some do, but most don't. So by lifting the kubelet configuration into the control plane, we make it more visible and in many cases more convenient to manipulate. There are certainly ways to dynamically configure a kubelet in Kubernetes today. Some people just SSH into nodes and manually mess with things. Some people use third-party configuration management tools, but really none of these ways are built with Kubernetes in mind, and they don't have a first-class user experience around them. Can I have the next slide, please? So what is dynamic kubelet configuration? Well, in Kubernetes 1.10, we launched the ability to configure the kubelet via a structured versioned Kubernetes-style config file API, as opposed to using command line flags. And so to use this, you simply pass the path to this file to the kubelet. And in 1.11, we launched this dynamic kubelet configuration feature to beta, which is basically just a way to deliver this config file in a live cluster to a live node and have the kubelet switch to using the new configuration. So you use the exact same structured version Kubernetes style config file format as the file you would normally just write locally, but you can post this config file into the Kubernetes control plane via a config map, and then you can tell nodes to refer to that config map that contains your config file. And once you tell the node to refer to it, the kubelet will download that config and restart to use the new configuration. Can I have the next slide? So before we get into the low-level details of what the API for this looks like, let's just go through a high-level workflow from a user standpoint to reconfigure a single node in their cluster. So the first thing the user would do is to write that config file and post that config file in a config map to their cluster control plane. And then once the user has done that, there's a field on the node object in spec called config-source.config-map that the user would update to refer to that config map. That field is effectively an object reference. So once that field is updated, the kubelet associated with that node object is maintaining a watch on that node, and so it will see the update, and it will then go find that reference config map, download it, unpack the files in it, and store that locally as what we call a config checkpoint internally. Once that config is checkpointed, the kubelet will restart to try the new config checkpoint, and then depending on what happens, the kubelet will update the node status and say, yes, I'm using this new config, it's great, everything is happy, or the new config didn't pass my validation, for example, so I'm going to report an error here, and I'm just going to fall back to the checkpoint I had previously until you fix whatever the problem was, so that I don't disrupt your workloads. So this workflow extends to multi-node rollouts. Instead of simply updating the spec for one node, you update it for all the nodes you want to refer to the new config map. Because you have control over which nodes refer to the new config when, you can control the rate and policy surrounding that rollout. Can I have the next slide? So there's a lot of detail on this slide. This is an example of the actual objects in the control plane that we're dealing with. So you can see on the right, we have the config map that contains here in the slide a truncated kubelet configuration. The kubelet configuration space is actually quite large. There's roughly 100 fields. And on the left, we have the node object that's being configured in this example. And in the spec for that node object, you can see that there's the config-source.config-map field. And in that field, we're just specifying the symbolic information that's necessary to refer to the config map, and also note that we're saying which specific key the kubelet config file of the config map is in. And if you follow the red arrows, those match up with the config map there. And then in the status of the node object, you'll actually see there's three sort of config source representations there, and those are you can think of those as the three things the kubelet cares about. So the first one is simply what the kubelet believes it has been assigned to use, and that's sort of like an ACK. Like once the kubelet has downloaded a new checkpoint and recorded locally which checkpoint it's supposed to use and come back up, it will report that. So you can see that it at least acknowledged, oh, I saw you reconfigured me. The next one is called active, and that is the configuration checkpoint that the kubelet chose to use at runtime for the current runtime duration. So the active can actually be equal to either the config source you assigned, or possibly the last known good config source if you assigned an invalid config, for example. So then the final piece here is that last known good config source. The kubelet does it basically waits for a period of time while it runs a config, and once it's run that config for that period of time, it says, okay, I'm pretty comfortable with this config. We might do more advanced things in the future to determine whether a config is causing too many crashes or something like that. But today it just validates the config and waits for that period of time. Once the config becomes the last known good, it's also reported in the status. And then finally, you can see the config map in this example slide has an error. Kube-API QPS is set to a string that is not valid. And so here that error, the fact that there was a validation error is being reported in the status as well. For pretty much all the validation errors and other kinds of errors that can be reported in the status, if you just search the exact same text in the kubelet log, you'll get a more detailed log message. A few different notes on this stuff. So the node status is explicit regarding the UID and resource version the kubelet actually downloaded, since like technically all this stuff is mutable in your cluster, and you want to be able to tell if maybe somebody changed something when they shouldn't have. And we specifically don't have the ability to like pin the symbolic information in the spec to a UID or a resource version for a number of reasons. One of which is that it's impossible to statically specify these versions because they're assigned by the API server. In addition to that, the fact that there's no real history that's easy to query for like, oh, give me this resource version of this resource means that it would be very hard to debug what the actual intent was in a live environment. If you do require versions on your configuration, we recommend that you inject version information into the name of the config map that you post, and ideally treat that config map as immutable. There's a kube control flag called --append hash when you're creating config maps that can help with this by appending a hash of the data in the config map to the name when you create it. Can I have the next slide? So we don't live in a perfect world. So there are plenty of gotchas with all kinds of things. One is that the configuration API is a little bit low level. So because we're using the same file format, this lets you set the whole config dynamically, but this is powerful and you should be careful. Some things are very safe to change, like QPS. Some things you probably shouldn't touch, like the names of C groups. There is inline documentation at the link in this slide for per field advice on which things you should be more careful with. So if you follow that link, you can find more information. And just as a reminder, the intent of this feature is to target system experts and service providers who can qualify these kinds of things and understand the system very well. Another gotcha is that we are moving to this config file API from command line flags, and so there are still a lot of command line flags that are deprecated but not yet removed and can still specify the same information as in the config file. For backwards compatibility reasons, these flags take precedence if they're still specified on your command line. So you do need to know a little bit still today about how your node was initially deployed to understand the full spectrum of configuration applied to it. We're hoping to reduce that service area in the future as we migrate these flags. So can I have the next slide, please? So these are just some thoughts on future work. As I noted in the previous slide, there are a lot of low-level knobs in configuration today. This is the case for both the kubelet and a lot of other components. Most users actually want high-level policy. When users tune different configuration parameters, they're not just doing it like for the heck of it, they actually have an end goal. They're trying to optimize for something. So, one open question is, can we have or offer high-level opinions or, named strategies that satisfy common use cases and tuning cases? Are there high-level principles that work for everyone that we can just bake into our components instead of exposing knobs to tune things? The higher level we can make these configuration surface areas, the friendlier the system will be to non-experts and also experts. So another item is that dynamic kubelet configuration is a manual per node configuration process. So there's no node pool type orchestration built in, but the Kubernetes cluster API effort is focused on solving this among many other issues, and you can follow that link to find out more about that. And of course, we are continually migrating away from flags into these versioned config file APIs. And then just one more slide here. Just the next slide, please. Yep. So these are some other links you can follow. The first is the blog post with some details on dynamic kubelet configuration. The second two are the official Kubernetes documentation for using the feature. In addition to the file-based config API feature. This third link is a doc on the philosophy behind why we should use versioned configuration files instead of command line flag APIs. So if you're interested in some of the rationale behind this migration, I'd recommend reading that. And then the final doc is just a general document on the API philosophy behind Kubernetes, given that we're migrating all this stuff to Kubernetes style APIs. That's one of the primary motivators. Thank you, everyone.
Great, thank you, Mike. So now we're passing to the storage area, and storage is yet another important area in Kubernetes. Those who are following our Kubernetes release webinar series could notice that we are constantly highlighting the storage features here. And now I'd like to invite Hemant Kumar from SIG Storage, who will speak more about resizing persistent volumes.
Hello, everyone. Hemant here. I'm going to talk about resizing persistent volume. This is something we introduced in 1.8, and we are introducing as beta in 1.11. Next slide, please. Okay, so what is persistent volume? Persistent volumes provide a storage layer in Kubernetes, which is useful for running applications that need to persist their data, and like for example, databases or Prometheus or applications that need state. There are three building blocks of persistent volumes. If you're not already familiar with them, like storage classes, they are like templates from which persistent volumes are created. Persistent volume is your also called PVs, or actual cluster scopes, volume objects which tie to like underlying storage. And then there's a persistent volume claims, which is basically a user managed object which user can use to create persistent volumes. Again, a storage class and persistent volume are cluster scope resources, and persistent volume claim is namespace resource. That is something that claim is what most users typically work with. Next slide, please. So what problem resizing solves? So one problem is that once we provision PV and PVCs, they remain a fixed size throughout their life cycle. And as applications that use them need more storage, it becomes essential to move them to larger PVs. And that can be tricky. Typically you have to like manually create PVCs, back them up, and then delete older PVCs, and then restart the pod that we're using them. It becomes kind of challenging. For stateful application, it becomes even harder because the PVCs are generally tied to the pods. Next slide, please. So what does resizing persistent volume mean? It means like in-place expansion of volume by editing the persistent volume claim object. Any user can go ahead and edit the PVC object and get a new updated volume that has new size. We do not support shrinking or reducing size of persistent volumes. And when we say resizing, then we expand both the remote volume object, which it could mean like EBS volume, or it could mean GCPD or Ceph-RBD volume, and it also expands the file system on the node. In Kubernetes 1.11, we support like these volume types: EBS, GCE, Azure Disk, Azure File, ClusterFS, Sender, Portworx, and Ceph-RBD. One exceptional case is that generally to require file system expansion, you have to restart the pod. That's something that we'll cover in detail in next slides. Next slide, please. So how do we expand persistent volumes? As I mentioned, the feature was introduced as alpha in 1.8, and in 1.11 it's going beta. But a cluster admin must opt in for this feature by or like enable expansion of PVCs that are created from storage class which has allow volume expansion set to true. Only PVCs created from the storage class that has allow volume expansion is allowed to be expanded. Other PVCs are by default not allowed to be expanded. This is to ensure that cluster admin has hooks and knobs so that the users are aware and the feature doesn't become available to everyone. Next slide, please. So how do we expand persistent volume? It's pretty simple. You just need to like run kubectl edit PVC and then PVC name, and in your editor you can just spec resources, request, and storage. Like you can see, you can request like you can edit the size, make it from by default 5 GB it was previously, and I'm requesting 10 GB. So it will expand the volume. The status is still showing 5 GB because the original volume is 5 GB. So you can go ahead and edit your PVC and save the PVC, and the resize process will start. Next slide, please. So after editing PVC for shared file systems like Cluster.fs, Azure file, if you have a pod that is using the PVC, the expanded storage is immediately available to the pod. There's nothing else you need to do. The pod should have the new capacity. Everything should work as it is, no problem. But for block storage volume types like not EBC, sorry, EBS and GCPD and Azure Disk, you will have to restart the pod so that the volume could be expanded on the node. So that's one prerequisite of so for the complete resizing process to finish. Next slide, please. Expanding file system requires restarting the pod, and once underlying volume has been resized. So the steps generally we do is like edit the PVC to request more space. Once underlying volume has expanded by the storage provider, then PVC will have this condition, file system resize pending condition. And as you can see that in this case has this condition, file system resize pending, and then wait for the PVC to have that condition and restart the pod. The pod could be restarted by deleting and recreating, or by scaling down the deployment and scaling up. And once you've done that, the PVC should come back with the pod should come back with the new size available to it, and it can use that additional space. Next slide, please. As I mentioned earlier, in Kubernetes 1.11, the volume resizing graduates to beta. As a result, it's enabled by default, and you no longer have to enable a feature gate. But Kubernetes 1.11 also introduces a new feature called expand in-use persistent volumes. What that will do is, in previous slide, you could see that we have to restart the pod, delete and recreate, or scale up and scale down the pod for the file system resizing to be finished. But if you have this feature get enabled, which is an alpha feature, then you don't have to do anything. The file system will be automatically expanded on the kubelet, and the new size will be available to the pod. One thing to keep in mind is that automatic file system expansion only supported for volumes that are in use by a running pod. That means this Kubernetes itself will not schedule the volume to a node so that it can be resized. No, it won't do that. You'll have to, for the automatic online expansion to work, there must be a pod that is using the volume. And next slide, please. So we are also working on enabling volume expansion for CSI. There's a link there, and then we have 1.12. We are also working on enabling volume expansion for Flex, and we are trying to improve the general stability and improving the file system expansion support. So those are some of the future works we are planning. Next slide. And you have we have some the persistent volume documentation in Kubernetes covers volume expansion, how it works, and the blog post, and there's how the persistent volume expansion will work for CSI. There's a pull request that you can have a look at it. So Yeah, I think that's all from me. Thank you.
Thank you, Herman. So now it's a Q&A time. I'd like to remind you that you may ask your questions in the Q&A section in the webinar software interface. Also, I'd like to remind you that this session was recorded and will be available soon at CNCF.io website in the events section. So let's start from the existing questions. So the first question is from Sudeep. So is the Kubelet and Kube-proxy both running as pods? I'm not sure who is the right person to answer this. Probably Mike.
Yeah, I know the answer, so I can answer it. So typically, the kubelet in most Kubernetes deployments does not run as a pod. Kube-proxy, however, does usually. A lot of people run it as a daemon set. I can also answer the most recent question. The answer, which is, does dynamic kubelet config mean that we run kubelet in a container? And the answer is no. Dynamic kubelet config is necessitated by the fact that we don't run the kubelet in a container in most cases. If you did run the kubelet in a pod, for example, you could potentially plumb config to it via config map volume source, which is how most people dynamically configure workloads with config files, but we don't do that, so we don't get that channel. Thanks.
Thank you, Mike. So another question is about the storage error. So I'm is the best person to answer here. So volume expansion also needs feature gate enabled. So does it need a feature gate enabled?
No, in 1.11 we have the feature is in beta, so it's enabled by default.
Great. And another question is also about storage. So what if the serve RBD already had extra space and we only partially use in our PVC?
It depends, like when we expand the volume and like what user has requested, like let's say user is requesting 10 GB space and the Ceph RBD was already of 10 GB space, then the operation is basically a no-op, and not no-op, but it will consider the expansion as successful and it will finish the entire operation. So, but if like, let's say the user is requesting 10 GB and the underlying Ceph RBD volume has 8 GB, but you have used only 4 GB, but Kubernetes doesn't know that there's still 4 GB free on it, so it will still try to expand the volume to 10 GB that user has requested, and it will go through the whole resizing, the volume expansion workflow, and it will finish the resizing process.
Right. Thank you. The next question is more general question and about the performance of Kubernetes. So probably someone here, anyone from the current presenters may have an answer. So please also update on any performance benchmarking tools and reports that are available for production usage of Kubernetes. Like, what is the maximum number of physical service can be used, and how many pods it supports, and how many VMs can be used? I can start from the latest part. So, what is the maximum number of servers or nodes can be used? So, officially today, Kubernetes supports up to 5,000 nodes in a single cluster. Probably someone here has any insights on the benchmarking tools for Kubernetes.
So we don't have anyone from SIG Scalability here right now, but there's active work in kind of expanding that and building tests around expanding that capacity. There is a link that I'll pop in the chat around building large clusters. So I'll just read off some of the high level notes. So at Kubernetes 1.11, Kubernetes supports clusters with up to 5,000 nodes. More specifically, we support configurations that meet all of the following criteria. No more than 5,000 nodes, no more than 150,000 total pods, no more than 300,000 total containers, and no more than 100 pods per node. What I can say about, so we have limits that you can set on the kubelet that will allow you to tweak both the maximum pods per node as well as the maximum pods per core. From let's say an OpenShift perspective, supports 250 pods per node by default. But again, this is a flag that you can set. We have seen clusters push 300, 500 pods per node. From the pods per core perspective, it's more arbitrary depending on the applications that you're trying to design. It's more of a, let's see the application run unbounded and then decide what we want to do from there. That'll give you a better idea of what your benchmark can be. But we do, I can say from the SIG scalability perspective that we do run tests, and we have been integrating more of the scalability tests within the test suites. So you'll see more activity in that in the future releases.
Great answer, thank you. Let's move on to the different questions. So, will the official supported Docker version change somewhere in the future? Probably, Mike, since you're working on a SIG-Node, you have some thoughts about this.
Yeah, I mean, like if you're looking for specific timelines, I don't know anything. Like the general answer is yes, probably, because it does change periodically. But yeah, I don't really know more than that. Sorry.
Yeah, no problem. It's a bit out of scope of our current webinar.
Yeah, just so I'll pop in one more time. Yeah. So just from a Docker and runtime supportability standpoint in general, you're going to see more and more developments around the community moving to the idea of OCI compliant containers. So not just Docker, but everything that supports the OCI spec. So watch news around cryo, which is kind of what we're going to be moving towards.
Great, thank you. Another question is, does anyone have any thoughts concerning the Knative components? I would say that Knative is totally out of scope with the current webinar. At the same time, I would encourage you to visit the Kubernetes users mailing list and discourse for Kubernetes to discuss this question with the community members. So, any other questions to our current presenters about the Kubernetes 1.11? We have a few minutes more here. Nope. So I don't see any extra questions in the Q&A section. So thank you for joining us today. I'd like to remind you that CNCF webinars are happening every Tuesday, exactly this time in your time zone. So please join us next week for the upcoming webinar. Thank you for joining us today, and goodbye.